Hi, and welcome to a video on indeterminate forms and L'Hopital's rule. So let me go through a little background here of what we learned in previous courses and what we've even been talking about a little bit in calculus so far. If I have 0 divided by some non-zero number, we know that to be 0. If I have some non-zero number divided by 0, we know that to be undefined. And again, I promise I'm going somewhere with this. And if we have those 0 divided by 0, what is that? Well, sometimes you learned that, okay, well, if you have 0 in the numerator, your answer is just always 0. And other times you had, oh, okay, well, if there's 0 in the denominator, it's always just undefined, which we know better in calculus because if the numerator and denominator is 0, it was most likely a whole. And so we had to figure out some way to evaluate that limit so we could evaluate where the whole is. Now we also had something else mathematically that said if you take a number and you divide it by itself, you should get 1. So why isn't that true for 0 over 0? We can't be 0, undefined, and 1 all at the same time. So which rule sort of applies? None. So we call this indeterminate. Basically saying I can't determine it right now. And L'Hopital figured out a way that we could evaluate that limit and figure out what it goes to. Is it approaching 0? Is it approaching 2.3? Is it approaching infinity? Where is that going? And so that will allow us to figure out that question mark or that y value of where is this function going at that point. Okay, so there are actually a bunch of indeterminate forms, but for L'Hopital's rule, there's only 2 that are going to be used. So we're going to talk about infinity over infinity because that is not 1. And then, because you can understand infinity is just an idea, so it's not 1. They're not necessarily the exact same size. And then we'll also talk about 0 over 0 for the reason I just mentioned before. There are other indeterminate forms, though, that we will look at, but it's very important to note that for L'Hopital's rule, you need infinity over infinity or 0 over 0. And then I'll show you what L'Hopital's actual rule is here in a second. So other indeterminate forms that we will study is infinity minus infinity, and you can probably understand that because let's say I take all the numbers from 1 to infinity, so I have an infinitely large set. And let's say I subtract just the even numbers. So if you have all the numbers and you subtract all the evens, which is still an infinitely large set of numbers, you have all the odds left. Well, all of the numbers minus, so an infinite amount, minus another infinite amount does not add up to 0. You still have some left in there. Sometimes infinity minus infinity might be 0. Other times it might be 1 or 1/2, but we don't know exactly what it is because, again, infinity is just an idea or an approximate amount, a really big amount. It's not exact, so we can't say that infinity minus infinity, we don't know what it is. So L'Hopital's rule can help us, but not in that form. We would have to make it be in one of these 2 forms, infinity over infinity or 0 over 0. Now 1 to the infinity, you might be thinking, why is that indeterminate? Because I know 1 to anything should be 1. You're repeatedly multiplying by 1. Well, there's 2 things that we need to look at then. Let's look at what's called exponential decay. So if we have an exponent, if we have an exponential function and our base is less than 1, this is exponential decay. And so that looks something like so graphically. And over time, this is heading to 0. Okay, well, if I have just a little bit bigger than 1 to the infinity, This is now bigger than 1 as a base, so this is exponential growth. So this looks something like so. And so that goes up to infinity. And so what we can see is if it's not exactly 1, if it's just really, really close to 1, I can't tell if I'm approaching something like 0 or if I'm approaching something like infinity. And because we're going to be doing these within limits, it might not exactly be 1. So I need to be careful with that. 0 to the 0, well, that's because it violates 0 to what we've said before. Any power should be 0, but we also said anything to the 0 should be 1. So we need to look at that. 0 times infinity and infinity to the 0 are also indeterminate forms. So if a function is of the indeterminate form only infinity over infinity or 0 over 0, then we can use L'Hopital's rule. And what L'Hopital's rule says is, and I'll kind of write it out for you here, the limit of the ratio of the functions f of x over g of x. So we're seeing these as two separate functions as a ratio, okay? F of x over g of x. The limit of the ratio of those functions as x approaches a in this case will be the same as the ratio, or the limit I'll start with, of the ratio of the function's derivatives. And that's where we got the f prime over g prime as x approaches a. So what that means is if I look at the limit of this ratio, f over g, and again, I'm still approaching a in both. I'm not going to change where I'm looking here. Then this is equal to the limit of the ratio of each derivatives. So L'Hopital proved that the ratio of the originals, that limit is going to be the same as the limit of the ratio of their derivatives. He is not suggesting that as a function these would be equivalent. He is also not suggesting that the derivative of f over g is f prime over g prime. That is not the case at all. This is only within limits, and this is only when we are of that indeterminate form. So let me show you how this works. And again, this is not the quotient rule, okay? And I wrote it out and typed it out if that is better for you. The limit of the ratio of the original functions is the same as the limit of the ratio of the function's derivatives. You'll have to probably read that a few times before it kind of sinks in here. So here's an example from start to finish. Let's look at it. So it says find the limit. So the first thing that you are expected to do is to substitute in the value. Because remember, if we can just substitute in x equals 1, into our problem, then we have no problem evaluating this limit. But when I do that, I got natural log of 1 over 1 minus 1, so I got 0 over 0. My check mark tells me, okay, that's what I needed. Now I can use L'Hopital's rule. And I use this notation here. Everyone does it a little bit differently, but in no way do I want you to think that this function right here is equivalent to this new function. It is not. I'm saying the limits will end up being the same. So I took the derivative of the numerator, so derivative of natural log of x is 1 over x, and then the derivative of the denominator is 1. And then you try substituting again. You cannot use L'Hopital's rule unless you have infinity over infinity or 0 over 0. So because now I'm over 1, I probably cannot use L'Hopital's rule anymore. So I'm hoping that I can just substitute in 1, and I can. I get a 1. So what that means is I have a hole at 1, because that was my x value, right, that I was approaching, comma 1. So I found this limit using L'Hopital's rule. The other thing that I will say is all of your Chapter 2 limit algebraic knowledge is still on your side. So if you can do a limit using Chapter 2 limit properties, whether you just do algebraic substitution, so maybe it's a factor and reduce, maybe it is a rationalize, something like that, certainly you can do that. And that's what I want to show you in number 2. So in number 2, we actually did this limit in chapter 2. So if I'm looking now for the limit as x approaches infinity, and I have these, we did this 2 ways. We divided through by x squared over x squared, or we talked about at infinity, only the highest powered terms are going to matter. Certainly that one being negative does make a difference. And so we would have said from chapter 2 that this is negative 1/2. And if you know that, you are done. If you would like to sort of prove that, here we go. I can use L'Hopital's rule to help me. So when I substitute, and now infinity is going to look the same as negative infinity, but I'll show you what I mean. I'm going to put infinity, so I have infinity plus infinity squared. That's definitely infinitely big. And then I have 1 minus 2 times infinity squared. So yes, this will be 1 minus some infinitely large number. So technically it is negative infinity, and L'Hopital's rule is not necessarily worried about whether it's positive infinity or negative, just one of the infinities, and you can use this. So now I'm going to apply L'Hopital's rule. And so I'm going to write limit because it's very important. If you aren't writing limit, you're trying to say that these functions are equivalent, which isn't necessarily true. I'm going to do the ratio of their derivatives. So the derivative of my numerator is 1 plus 2x. And the derivative of my denominator, the 1 will go to 0, and I will have negative 4x. And I try to substitute in infinity now. Well, it's still infinitely big in the numerator and negative infinity in the denominator, so I'm going to do L'Hopital's rule again. No problem. So L'Hopital's rule. And sometimes you have to do it a few times, and that's okay. It's called an iteration. It's like how many steps do you do it. So the derivative of my numerator is 2. And the derivative of my denominator is 4, I certainly cannot use L'Hopital's rule anymore because I don't have an indeterminate form. I know what 2 over negative 4 is. It's negative half, no matter what x is. And so I knew negative half from the beginning, but now I just sort of, I'll call it proved it, using L'Hopital's rule. So here we go. Trig, right? And then we'll get to the y here. So this one is sort of a basic trig one, just to get you started thinking like, gosh, it doesn't look like it's ready for L'Hopital. Well, if you think of cosecant x as 1 over sine x, because cosecant is reciprocal of sine, and if you know your basic identity for cotangent x, that it would be cosine x over sine x, I do see that I could have a rewrite here. I have common denominators already, and so I can rewrite this problem. If I substituted directly without combining this, I can probably see it as well, because I do have, when I substitute 0 in for x, sine of 0 is 0, and then sine of 0 is 0. So I have 1 over 0 minus 1 over 0. I know that doesn't necessarily maybe make sense to you, but if you think about it, you have common denominators, and so subtract your numerators. So this is 0 over 0. Or you could combine it like I did into one fraction and then substitute your 0 in. Cosine of 0 is 1, sine of 0 is 0, and I can see it that way. So let's use L'Hopital's rule. So see, trig is not scary. Trig's one of my favorite things. Okay, so derivative of the numerator, be very cautious because with trig, sometimes we forget our derivatives of constants go to 0. So the 1 is going to fall off. Derivative of negative cosine x is positive sine x. Watch your positives and negatives. I'd say watch your sign, but then I'm dealing with the function sign. So then derivative of my denominator, derivative of sine x is cosine x. Yes, I could rewrite this as tangent, but again, I don't know that you have purpose for doing that, because if you rewrite that as tangent, you might not be able to evaluate it like you want. I don't know. I just think it's easier to see it as a ratio, especially if you have to do L'Hopital's rule again. So sine of 0 is 0. Cosine of 0 is 1. And be careful, I can absolutely evaluate 0 over 1. It is 0. And so, yes, this is a coincidence that once again my x value matches my y value. But what this says is that you have a whole, right? So if you can evaluate the limit at that value, it's a whole at 0, 0. And so why are we even studying L'Hopital's rule? Here's a couple things. It will absolutely enable us to find limits that we could not previously determine. So from chapter 2, we couldn't do every limit out there because we were kind of limited just to algebra, and now we've got some calculus to help us. And it will enable us to find the hole in the graph, so we can look, and remember, we're working towards being able to get a function and graph it without the use of technology. So this will tell us where a function is going at certain points. Okay, and probably last one for this video. So what I showed to start with, we're looking now for the limit as x approaches infinity of a product. And while I might recognize that that might be an indeterminate form, it's not necessarily ready to use L'Hopital's rule for. So what I did is I just substitute in infinity. So it kind of looks like infinity times e to the negative infinity. And what we know is that a negative exponent, right, can move that power, base with exponent, to where it needs to go. So if it was a negative exponent in the numerator, it gets reciprocated and that power gets put in the denominator, and now it has a positive exponent. And so now I do have infinity over infinity. But what's important to note is that you should rewrite your original so that it also looks like this fraction, because otherwise you really don't have a ratio. I don't see a ratio here. So I'm going to keep the factor of x where it is, but this is the one that we moved right when we evaluated it. So I'm going to move it now when it's e to the x. And so now I can apply L'Hopital's rule, because I've proven that that is infinity over infinity. And now you can probably see it a lot better as well. Keep writing the limit. If you don't write the limit, you're not actually applying L'Hopital's rule. You're probably doing something very illegal. For those of you also moving on to Calc 2, I would like to say L'Hopital's rule becomes a pretty big deal, and it's in, I don't know, I'd say probably 20 to 30% of our problems for the whole semester. So it is something that is used often. Because we need to evaluate these limits. Okay, so let's apply L'Hopital's rule. So I'll do the derivative of the numerator is 1. Derivative of the denominator, derivative of e to the x is e to the x. And then stop and try to substitute. So if I do that, I can put infinity in. I get 1 over e to the infinity. 1 over something really, really big will go to 0. And this isn't necessarily a whole, because now x is going to infinity. So this will tell me a horizontal asymptote as x approaches positive infinity. So that's one other enabling here, is that even if it's not a defined value like a whole, it enables us to find horizontal asymptotes. And so I'm just going to put as x approaches positive or negative infinity. Okay. So we're going to do some more in the next video, maybe some more, I would say a little bit more challenging problems where maybe it's either not ready to go right away for L'Hopital's rule, or maybe you need to do it a few times. And we're also going to use L'Hopital's rule to actually show what E is. So I think you'll find that challenging, but also helpful to understand where that comes from. I hope you found the beginnings of L'Hopital's rule helpful.